Today's lecture is a little bit technical in nature. I want to cover some of the very fundamental concepts underlying how data is represented and manipulated in R. My goal is not to cover everything about programming, just to give you some very fundamental concepts, enough to build on as we go along. This is chapter 4 in the textbook, and I cover a little bit different things in addition, but um, all the code and the data that I use today are in the RStudio project, lecture 04, this lecture. I'm going to work entirely in RStudio today. Uh, that way I can give you some tips about how to operate in that environment. Okay, so in a few seconds here, we're going to instantly transport into RStudio right. Here we are in RStudio Cloud. I've signed in as my favorite student. I am Deadpool. You'll remember that you need to go to your workspace, check data science. You'll see that I've made a project L04 available. You need to make a copy of that. Okay. As a note, while it's deploying here, sometimes when I try this, I initially get a something that says I don't have permission. If you try it again, it seems to work. I think it's a small bug in the cloud. While we're waiting for it to deploy, don't forget that you need to save the temporary project by hitting Save a Permanent Copy. Okay, so we're ready to go. Let's go to examples, and this is the small R um, script that we'll be looking at today. Okay, so here we are. I'm not going to use these windows very much, at least at the beginning, so I'm going to minimize them a little bit, give us some more space over here. Okay, so let's begin. This plus is an operator, okay? Um, and 5 and 6, whoops, uh, sorry, 5 and 6 are operands. Operators operate on operands. A little bit of terminology to keep straight. So I can do all sorts of things here. I can use Command C, paste it into the console with Command V, in Apple at least, and you'll get the plus. So we also, if I want to run something, I can use the button run here with the cursor on that line. It'll just run that line, 5 minus 6. The asterisk is multiplication. Now, another way to run it, at least on the Apple, is to, on a Mac, is to use the command return, and that executes just that line. Division, okay, and this caret is exponentiation. So 5 caret 6 is the same as writing 5 to the 6. Okay, all right. Uh, the hashtag represents a comment, and um, if I paste that into the console, R just swallows the line and doesn't interpret it. So basically, comments they're put in to make the code more readable. So sometimes you have a complicated expression or um, some kind of logic that you want to use natural language to help another person understand. You put a comment in there. Also, just to remind yourself what certain variables, etc., meant. Okay, so one thing that you're going to see an awful lot in R is the idea of a function. Or not the idea of a function. You're going to see many functions, and there's a lot of built-in functions. For example, sine 5. It gives you back the sine of 5, a real number. Okay, so a little bit of terminology here. I don't really want to give you too much terminology. Um, that's not really our focus, but we say that the sine function takes a parameter, and that in this case here is a real number. Okay, now a function has really three things. It has a name, in this case sine. It has these parentheses, okay? Those are those round brackets. Now that's really important. Um, I'm going to even write this out here, parenthesis, okay? Um, oops, parentheses, this. Okay, those round brackets are not the same as curly brackets or square brackets, okay? So, and the third thing about a function are the parameters, what it takes as input. Okay, so here we say that 5 is passed as an argument to the function sign, okay? The output of sign with the parameter x is the sign of x. Okay, so here's a useful concept from computer science. We often think of functions as being black boxes, okay? We would label this box sign, okay? And it really has its parameters and its output, or we sometimes say the return value, okay? And so, 5 in this example is an argument whoops, I'm sorry, is an argument that's assigned to the parameter uh, x in that function, and it returns then the sign um, of x. Okay, so why do we call this like a black box? It's because we don't care really what happens in that function. Some geek programmed the sign function for you on a Friday night because that's what she likes to do. But we really don't care how that's implemented or how it's done. I mean, they just ask God for the value of the sign of X. For all we care, what we care about only is just that we know what to pass to that function and what we're going to get back from it. So it's called black boxing because we can't see into it. Maybe a better word is an opaque box. Okay. And there's many, many functions in R. Cosine, not surprising, tan H, the log function here, the log of 5. You could ask, well, what's the base of that function, right? And by default, the base is E. Okay. So um, now before going on, I should say that there is really an awful lot of functions in R, and almost any mathematical function you can think of is probably already been programmed into the language. So a little bit of searching on on the web, and you'll find uh, probably a package or a function that computes that whatever it is that you're interested in. Okay, so well, one thing here is that in this example, uh, the log was computed, 5 was computed relative to base E. If we wanted to change the base, the log function in R accepts a second parameter. Okay, so here the second parameter uh, is the intended base for the logarithm. So here's how we would write it. Um, we could say the log of 8 base 2, and that's 3 because 2 to the 3, whoops, 2 to the 3 is equal to 8, right? Okay, so to go back over to here just to write it out, so the log base 2 of 8 is equal to 3, right? Because 2 to the 3 is equal to 8. Now, I'm using this example here. It's really boring, but it's important to basically describe how parameters and arguments are bound to parameters in R. So this is really fundamental. So here I've actually labeled the second parameter explicitly as being the base. Um, that tells R that the second parameter is the intended base for the logarithm, and I can change that to 4, or I could change that to natural E. So for example, here, this should be exactly the same. Oops, what happened there? It seems that RStudio Cloud puts this period after functions. I don't know if that's just my machine, but if somebody figures out how to get rid of that period showing up when I hit double space, um, I think that's definitely a +1 for the class, right? Okay, so that's the same as the default of just log 8. Okay, so the default is base E. And for example, here I could say, what is the log of 6.5 to the 27, base 6.5? Well, I mean, it's a silly example, right? But so the log base 6.5 of 6.5 to the 27 is just going 6.5 to the 27 is just going to be equal to 27, right? Um, that's just kind of high school uh, arithmetic. But okay, so what I'm really want to point out here is that um, uh, some functions take one, two, or more arguments. Okay, in fact, some functions don't take any arguments or any parameters. But how do we know about that? How did I know that base is the way to specify the base? And the answer is that I didn't. I used the help. So if I come in here and I ask for help on log, if I go over here now in the help section of the bottom right window, I see a description of the log functions in R. And these are the usage here is where it is. You'll get used to reading these things over time. Here you can see that one version has the base, the log function. It has this parenthesis that delimits the parameters. The first one is called x, and the second one is called base. And then it's got this notation here that base is equal to exp1. That's the way it's been programmed by the geek who did it in the first place. And that indicates that the default value, if you don't specify a base, is going to be e. I want to make sure that you understand that exp of 1 is equal to our famous e, right? Okay. So if you don't specify the second parameter, it just fills it in with this default value specified here, okay? Now for this, the log 10x, that's part of the function name, and it's been programmed so that you can't change the base. It's only ever going to be base 10, right? So if I ask, what is the log 10 of 10,000, I should get 5, or 10 to, oh yeah, sorry, 4, right? Yeah, there's 4 zeros in 10,000. Yeah, sorry, it's early here. All right, now um, here's another example. Okay, so not all the examples we're going to look at today are boring math, right? I mean, that's not the point here at all. It's just that it's a good place to start, maybe. There's other functions that are much more interesting. Like here's the seek function, okay? And the seek function, I passed it three things: 1, 10, and by is equal to 2. So there's three parameters that seek takes. Actually, if I want help on seek, I would just type in question mark seek. I can also write this as a function. The question mark, you can do this as an operator. So this is actually an operator that takes one argument, an operand, seek, and gets help. It can also be expressed as a function that takes one parameter, the name of what you're interested in, and they're completely equivalent. It's just for convenience. Okay, so here's the help for seek now. And the point here is this guy. And actually, it looks quite complicated. I didn't even know that seek had so many potential parameters. Many of them have um, default values of null. So, that means that you don't actually even need to specify them at all ever. So I never have. I don't even know what they do. But the main ones that I'm interested in here is the from is equal to, and the to is equal to, and the by is equal to. Okay. Now, basically here, if you don't specify from, then the default will be 1. And if you don't specify to, the default will be 1. And by is then going to be taken to be the result of this equation. So let's suppose both were equal to 1. This would be 1 minus 1 is 0. And so basically it's going to be 0. So there's nothing to do. That's just let's ignore that for now. Now, if I come over here, I could have, my original way I called the function, I just said seek 110, and then the third parameter was by is equal to 2. So basically what R does is it takes this 1 and it matches it to the first parameter, which is from, which makes sense because that's where we're starting from. And then this 10 gets matched to 2, and that makes sense because we're going from to something. And then the by is counting by whatever. In this case, we're counting by 2's. And that's matched to the third parameter by. Okay, that's actually pretty sloppy programming because although you can get away with that in R, it's much better to do it this way where you explicitly name your arguments to match the parameters of the function. This gives exactly the same output, 13579. But here I've explicitly said that from is 1, that's the bottom, and 2 is 10, right? That's now because they're specified in that order here, it'll still work, but it's dangerous. And if I look at this, if I do this, and now I change 2 to be 10 and from to be 1, now when I run this, oops, sorry about that. When I run this, I see 13579. Exactly the same thing occurred. So now 10 wasn't matched to the from, the first parameter. It was matched to 2 because I told it R, the first parameter here, the first argument, my 10, is intended for the parameter 2. And my second argument here, a 1, it's intended for the parameter from. And by has always been explicitly stated. So what if I were to do something like this? Seek 10, 1 by equal to 2. Now, what's going to happen when I do that? It's not going to like it. It's going to say, yeah, the by, wrong sign in the by argument. The problem is that once you're at 10, you can't go down to 1 when you're counting by twos. Now, if I were to instead put a minus sign there, I could put a minus sign and I'll get 10, 8, 6, 4, 2. Side note here. If you use the arrow keys, you can scroll back through your history. Okay, so the last thing I executed was this seek 10, 1 by equal to minus 2. But the point here is that when I submitted this to the seek function, my arguments here, well, my arguments 10 and 1 were because I didn't name them. R tried to match them to from and to in that order, and of course, you can't get from 10 to 1 by 2 by positive 2. Okay, so it takes a little bit of practice, but uh, let's suffice it to say is that I prefer I prefer this style. It's the safest style. Okay. Otherwise, you're making assumptions about the order that the parameters are listed, etc. It's just a safer way of programming. Okay, now variables. They're really important concepts in any programming language, really, because they really represent the fundamental concept of memory. Okay, so what do I mean by that? Well, here we read this statement as x, it's going to be called the variable, is assigned. That this less than dash is read as is assigned the value 5. So when I execute that, I want you to watch over here in my environment, okay? When I do that, suddenly I have a new value up here called x that's been assigned the value 5, all right? Okay, so that's the first example of a variable, but we got to go through that a little bit. Okay, so the point here, 3 things occurred when you assigned um, x to be 5 to x. The first thing is it created a location in its memory. It named that location x, and the third thing it did was put the value 5. Create the location 1, name it 2, value 3. Okay, all right. So 3 things occur. And you can think of this basically as being kind of a location in memory. Now, I'm going to give you a piece of advice that you're probably going to ignore because everybody seems to ignore it. Is but you should always have paper and pen beside you when you're programming. I like to draw out my variables like this. Now, it's true that in our studio, you have this really nice display called environment that tells you what's been assigned already. The thing is that once you start to get into complicated data structures, I don't find it to be um, complete. Sometimes I like to have really big data structures written out on paper where I can understand them at some sort of higher spatial level. Okay, well, you'll find your way, but I highly recommend drawing things out. It helps you to evaluate yourself what R is going to do. All right, so let's continue with our variables. I can make another one called y. And so what's happened here, of course, is now three things are put aside some space for a variable labeled 5, and then it puts 6 into that location. Okay, that's the three things again. And now I can use those x and y's as to do interesting things. For example, I can ask what's x times y and get the answer out there. Now notice nothing changed in my environment there. Um, you can ignore this from variable. I made a small typo and created a variable by mistake. Um, I think I can just do, yeah, okay, I got rid of it. RM is removed. You can remove a variable, destroy it. Okay, so just to simplify it. But notice that when I executed this statement here, nothing changed in my environment. I can run it again if you want, and nothing's ever going to change because x is still 5 and y is still 6. I can execute something like this, which says that z is assigned equal to x times y. And when I run that, I do get a new variable, z, which is equal to 30. So now I've remembered the result of computing x times y. Now that I think we should go over a little bit. So, what's happened here when it executes? What's it going to do? What does R do when it tries to execute this expression? Z is assigned equal to x times y. This is what R would do. R comes in and says, okay, Z, I'm going to need a new location, and I'm going to call it Z. Okay, I'll label it Z. Now, what value do I put in there? Okay, well, I have to evaluate this expression then. So what is that equal to? Well, X. X exists in my environment, and it has a value, so I'm going to replace that value, that letter X, that symbol, with the number 5. And I know what multiplication is. Okay, now, what is y? Does y exist? Well, it searches through its environment and says, aha, y exists. And it has the value 6, so I'll replace y with 6. And so now this boils down to computing 5 times 6, which is 30. And now it has to execute. Z is assigned equal to 30, and so it puts 30 into this square, into that location right there. Okay, so often uh, in tests and quizzes, I ask you to pretend that you are R to basically simulate what R would do on a piece of code that I give you. Um, I mean, the reason for you to learn to draw these things out and step through is not to just like, be prepared for assignments and quizzes, but it's for you to help understand what's going on in your own programs. Okay, so the semicolon here, it just allows you to put multiple expressions on the same line. It's just convenient. Instead of writing out, putting these guys on each on their own line, I can save a bit of like visual space by putting them on the same line. But I can't do that. R would get confused if I wrote that. It wouldn't know where the first expression ended and the second started. So the semicolon just says, okay, that's the end of an expression, all right? And I can run this, and when I do run it, I can put all three in at the same time. I see that XX was created, YY was created, and fraction was created as the result of XX divided by YY. Um, no problem there, I think. Um, okay, so why, or how did I choose the variable names x or xx, y, etc.? And the answer is it's basically arbitrary. You just call things. Well, you should use names that are meaningful. Okay, that's a kind of an important idea because as your programs get larger, it's really hard to understand your code. So names like XX and YY are really not good names, but um, fraction's a pretty good name because it is the fraction of XX and YY. Okay, but okay, so are there rules for what you can use as variable names? Yes. My first variable is perfectly fine. You can use underscores. You see it's created here. Some people will write it instead using what's called camel case. So you capitalize the first letter of each word. But you can see that they're not equal. They're two different variables in the system. I can't start something with a 1 or any number. You shouldn't start your variable names with symbols like periods and underscores, especially because R reserves some of that for system things. It's not really encouraged. But you can't use a number, it doesn't like that at all. I can put a number inside or at the end of my variable name, that's perfectly fine. Or I can do, you know, that, that's okay too. It doesn't mind those, and you can see that all of those variables are successfully created. So there's a little bit of constriction on what you do. The main thing is to try and use variable names that you know make sense, okay, and that you can understand what they are. And what happens, when I type in my first variable here, in fact, if I, as you know, probably by now, is that if I stop typing halfway through a word, our studio tells me what that might match, and I can just like tab and hit return, and it'll auto-complete my phrase. Okay, so my first variable produced the value of my first variable, which is 15, right? Okay, no surprise there. What if I give it a, um, a symbol that hasn't been defined yet? I mean, if I go to my environment, right, I don't see anything called king in there. So what happens when I do that? R objects and says king is not found in the environment. Now I can assign it and then ask, um, so here I'm assigning it. So I'm saying king is assigned. Now this is special. These these this is what's called a character. Okay, sometimes computer scientists call them strings. So I'm going to apologize right now. Is that sometimes I make the mistake and call them strings too here. But in R, the type is really should be called character. So this those quotes are really special because it tells R that I'm not intending to write a variable name. I'm intending to write not a string, a character. Sorry, there you go, a character um, that might be like natural language, for example. Why do you need characters? Well, usually your program is outputting in natural language so that you can understand, so that you can interact with the program, right? So it's a way of um, for your program to communicate with the human, sort of thing. Okay, so those quotes indicate that it's not true. This quote Mike, if I type in just Mike like that, it's going to give me an error because Mike doesn't work in my environment. However, if I put in quote Mike like this, it's perfectly fine. It says, yeah, okay, whatever, you gave me a character called Mike and Mike. So the same thing if I type in six, it'll just respond six, right? It actually it treats it as an expression, but there's nothing to do. So it just says, okay, I'm done. Whatever, what are you getting at, man? But yeah, okay. That's again very different than this. When I don't put quotes there, what R does is try to look that up in the environment and ask, does Mike exist as a name? And the answer is no. And that's why you get this error. Okay. Okay, shifting gears. There are some constants that are predefined in R. By predefined, I mean that as soon as you start up, they're there, like pi, okay, letters, A through Z. These things are just convenient sometimes when you're writing equations or you're trying to, write out text that for the program to communicate with the human, etc. Then there's some special symbols that you probably haven't really seen. I can have my variable is assigned equal to infinity. You'll see here now, over here, my variable is infinity. So you'll see that RStudio writes it in blue. It's highlighting to say that this is a special symbol in R. It has special meaning. For example, I can ask this, is 5 less than infinity? And oops, uh, and actually it responds, yes, it is, right? What about, is infinity less than 2 times infinity? And the answer is false. That's really deep, right? Uh, Whatever. So another special symbol is Na. And we're going to see NAs in a couple lectures from now more. We've already seen, I think, a little bit in the BRCA, the small BRCA data set. Often, if we don't know the value, let's say, of a clinical attribute for a patient, like we never took the measurement of their age, we don't, well, we have to put that into the database somehow, and usually that's represented as NA, meaning not available, right? Okay, so you could, yeah, it's kind of a placeholder. It says like it's, if the question was, what day of the week were you born? It has to either be Sunday, Monday, dot, 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 Saturday, right? But if you don't know somebody, the day that somebody was born on, you would write NA to mean it's not any one of Sunday through Saturday. Okay. Related to this is this concept of null. Now, okay, so one thing is that notice when I use the same variable name, my variable, I initially was set equal to infinity. Well, let's do this again. Yeah, it is infinity. And now when I execute and this one, its value changes. Now my variable is assigned NA. And if I do this, um, it switches to null. Okay, so that's actually the fact that you can create a variable and replace its content is really fundamental to computers. That's this notion of reprogrammability, right? That the code and the data that we have in our memory um, can be changed, right? That we can overwrite it and load one program up over on top of another one, get rid of the old one, right? So that this is really the core concept there of computation, which is reprogrammability. Another type of variable that's special, another symbol that's special is true. And I can actually just type in true here, and it comes back true. Same thing for false. These true and false form the basic for logical variables. So I can say, for example, my variable is assigned true. You see it shows up over there. And if I ask what that is, um, it says true. And I can say my variable 2, which is not going to be the same variable, is false. And so now you see that it's recorded as false. These are so-called logical, or what mathematicians would call Boolean variables. So they only take two values, true or false. All right. They could take NA, right? But that's basically a special case where if you didn't know the answer to a question that's yes or no, a yes or no question, you would say NA. But in general, Boolean variables only take these two states, true or false. And that's really key. That's a very fundamental concept in computers because this true false is the same as 1 0. And that's this nature, that's this discrete nature of modern computers, that everything is comprised of ones and zeros, right? So these are really, really fundamental concepts that in programming that are almost true of all programming languages. Okay, so here's a little challenge now that you've learned what variables are. Let's suppose that I've defined two variables, var1 and var2. Well, in fact, I'll create them. There they are right there, var1 and var2, with values 10 and 20 respectively. I want you to write a program that swaps their value. So after you write your code, var1 should have the value that var2 had, and var2 should have the value that var1 had. In other words, what we would want is that var1 has 20 and var2 has 10. Now, this code here doesn't work. And do you understand why it wouldn't work? Well, let's go through it over here. Okay, so we have two variables. Where's my color? Var1. Okay, and it starts off with the value, what was it? 10? No, oh my. 10. 10. And var2 starts off with the value 20. Now our goal is that they swap. So our goal, I'm going to write it here in orange. Our goal is that var1 has 20 and var2 has 10, right? That's what we would like. Uh, sorry, write this again. Apologize. We would like this guy to be 20 and this guy to be 10. That's our goal, right? How do we do this? Well, if I use the program from the previous slide, it isn't going to work. So if I say var, let's go back to the program, var1 is assigned var2, how does R evaluate that expression? Okay, it comes in and says, well, var1, I know where that guy is. This is assigned equal to var2. var2 exists in my environment. and I can look up its value. It's 20. I'll replace var2 with 20, and now var1 is assigned 20. And so now R writes a value 20 in var1. So far, so good. The second expression is that var2 is assigned var1. Okay, well, so how does it do that? Well, it says, okay, I know what var2 is, and it's assigned equal to the value of var1. Well, var1 exists, that's fine, and its value is 20. So now I assign var2 to be equal to 20. And so with that simple little program, it doesn't work because it doesn't swap the values. In fact, at the end of the day, they both have the value of R2. So I'm not going to show you the solution here. This is your classic first little programming challenge, is to try and fix that and find a way to swap the values in a fair way. And I don't mean here a program like var1 is assigned 20 and var2 is assigned 10. That's not a solution to this problem, right? Because you'd have to have a different, every time I change the values for var1 and var2 up here, you would have to write a different program to solve it. I want one program that solves it for whatever values I put up here, okay? All right, so we're moving right along here. The next thing is that there are some operators, recall operators like plus, minus, correct for exponentiation. Those ones you're pretty familiar with. And then there's some that you may not be too familiar with. Okay, so for example here, let's create 4 variables, 2 numerics, 5 and 7. Z is infinity and W is null. Okay, so they all get created, X, Y, Z, and W is there. Um, well, this one I think you should know. X is greater than Y. That's pretty straightforward. And in this case, it should be false. So notice here that the output, when I type in something like X is greater than Y, it responds by giving a logical, either true or false. And this one here is X less than or equal to Y minus 2. Okay, well, let's evaluate that. I know that this may seem very pedantic, me doing it this way, but X is equal to Y minus 2. The point is that doing it, a few of the, writing out what R would do step by step, helps you to learn how it evaluates things over time. So we had, in this case here, we have 2 variables. X was 5 and Y was 7, right? I think that's what it was up here, 5 and 7, right? Okay, so now what we want to do, how does R handle this expression? Well, it knows what X is. It exists in the environment and its value is 5. 5 less than or equal to, well, it knows what that means, those operators. Now, it knows what Y is. It exists in the environment. It's 7 minus 2. Well, it knows how to compute 7 minus 2, so it's going to do that. So this is now testing, is 5 less than or equal to 5? It is, and so it's going to respond true. Okay. Okay. And I think that should happen here, right? And then there's some weird things like, is X bigger than infinity? Nope. Is X bigger than null? Um, oh, there's another one of those periods. Is X greater than W? It says logical 0. So basically, this is kind of like it doesn't know how to respond to that, right? Like W is null, so it doesn't know. It can't really decide that question. W, it exists, but it doesn't have any value, so it can't evaluate whether X is greater than or equal to or less than W. So it responds in that weird way. Okay, now this is a really important concept. And a lot of beginner programmers make this mistake in R. Notice here the double equal sign. Okay, so this is asking, we read this as, um, is X equal to Y? Are they the same value? And in this case here, we know, no, they're not, because X is 5, Y is 7. But this is not the same thing as saying, uh, assign the value y to x, right? This is asking, it's just a test. It's like saying, is the sky blue? Okay, uh, right. Is it raining outside? It's just a test like that that answers yes or no. Well, true or false in computer terms. And likewise, or related to that, is this concept of not equal to. So the not, the exclamation mark is the not symbol in R. So this is read as is x not equal to y minus 2. These parentheses control the order of operations. We'll come back to that later on. But so here we're asking, is 5 um, not equal to y minus 2? That's 5 actually. So this should be false because it is actually equal to um, x is actually equal to y minus 2. Now notice the difference here. I want to make sure it's clear. When I write x is assigned equal to 11.3 and I run that, I get a variable that has the value 11.3. We assign it, right? If I do this, x is equal to 12.1. I'm asking a question, is x equal to 12.1? When I run that, I get the answer false because x is equal to 11.3. And of course, it doesn't change the value of x. It's like if I ask, is the sky blue? Um, uh, and the answer is false, it doesn't change the sky to blue, right? It's just asking, is it blue? Okay, so uh, then we have variables that are called logical variables, and you can assign those easily too, just like any other variable. And here I'm assigning me to be true and you to be false. So here I am me, and you're somewhere down here in the false category. Where are you? I don't see you. Where to go? Oops. Oh, these periods. There's an error. I'm sorry. Let me run that again. I don't know why what's those things RStudio's putting that in there. It only happens in RStudio Cloud. It must be a little bug on their system. I'll write to them today. Okay, so here you can see you is false and me is true. Now I can say not me. What do you think that does? The not operator. This is an operator, and it's a unary operator because it only takes one operand. In this case, it's taking the variable me, and that is going to be equal to false, right? Because not true is false. Right? So if we come back to how to evaluate this over here, we have that me is assigned true and you is assigned false. So not me is evaluated then as not true, which is false. Okay. So this gets into something called Boolean logic, and this is really important for making decisions in programs, right? And that's a fundamental property of computation. Recall that you can look at the state and memory of the computer and use that information to make decisions. For example, we had, if the sky is blue, I won't wear my jacket, right? If it's cold outside, I will wear my jacket, right? So if it's cold outside is an expression that evaluates the true or false. If it's true, I do one thing. If it's false, I do something else. So we need to have a language for asking those kinds of questions, and they're called logical expressions. Okay, so here I can test uh, the question. Oops, is not me equal to you? So what is that? Well, not me is false, right? So not me, whoops, is equal to you. Well, not me is not true, so that's false. And you is false, so false is equal to false. And so yes, the result of that expression is in fact true, right? Um, so that's false. So is false equal to false? Yes, it definitely is. So the result of the expression is true. And I can ask, now we get into some, um, the idea of logic gates, okay? And I don't expect you to understand this entirely at the beginning. but there's a special operator. It's a binary operator. It takes two operands, me and you. And the first one, the ampersand, is read as and. Okay, so I'm going to even highlight that there. This is an and. So this is going to be true, this expression, if and only if both me and you are true. Now, we know that in this case here, that's not the case because me and you, how is that evaluated? Well, me is true but you is false. And so it's not the case that both are true. And so the answer to this is false. Okay? So let's see, does that match what happens here if I put this into R? False. So what about me and not you? Well, let's go back over to here. I'll explain the intuition behind this a little bit more in a minute, but stick with me. So we're asking me and not you. Well, I'm true and you're not false. So that's equal to true. So true and true, it's true. And so this is going to be, whoops, true. What about not me and you? Well, not me is false. So false and anything else is going to be false because the and operator, this expression is only true with an and operator if both sides are true. So this is, and the second one here, not me and not you. Well, in both cases, I'm false. It doesn't matter what you are really, because once one guy is false, the whole thing is false. Why do we need the and operator? Well, it's really important because at times in your programs, you're going to have to say something like, if HER2 expression is above 10 copies and ESR1 expression is above 15 copies, then that patient's at risk, let's say, okay? So sometimes you want to say, you want to specify conditions that have to both be true for a certain uh, um, for something to be carried out. So if we kind of leave the computer world and just think about common sense, it would be something like a clinician saying, well, if the patient is estrogen receptor positive and she's above 65 years old, then I will prescribe tamoxifen, right? But no chemotherapy. So her decision making is based on the fact that both of those conditions, her age and the estrogen receptor status of her tumor, decide what's going to happen. Okay, so that's what the and does. Basically it's a way of specifying that everything has to be co-occurring in a sense, right? They all have to be true at the same time. Now, and we use and all the time in natural language, of course. Or is another example. And here it's a condition where you want to express the or is used as an operator. It's also a binary operator. It takes two things, me and you. When you want to say one of the conditions has to be true, they both can be true, and that's going to be a little bit different than how we use or in natural language often. So this would be something like me or you. Well, let's first evaluate that, okay? Uh, so me or pipe, you. Okay, so me is true and you are false, but it only takes one of them to be true, so the whole thing is true. Okay, so if I paste that in, then I come down here and I see me or you is true because I'm true, as long as one of us is true. If both of us are false, then it'll be false. So which of these four cases is the one where both of us are false at the same time? Well, let's see. This case here, me, I'm true. So this case is going to be true. The second case here. In this case here, I'm false. In both the third and fourth case, I'm false. Not me is false. So now I need the case where, now this case here, we're both false, right? I'm false and you're false, so that's going to be false. It is. This case here, though, I'm false, but you're true, and so it's going to be true. Now, this is the case that we have to be careful about, and I want to make sure we understand. In this case here, me and not you, me, sorry, or not you, okay, I'm true, or not you, which is true. Now, that we're both true, and when you evaluate that, it's true. So that's not necessarily how we use or often in language. Often we're implying either or. One of the two conditions has to be true. So this would be sort of like a clinician saying, if the woman is in good physical shape, um, or uh, she is less than 45 years of age, I will give chemotherapy, right? So this is the case where the clinician is saying basically, if the person is young enough, they're going to survive the chemotherapy. But they might be older, but if they're in good physical shape, I'll still risk it with the chemotherapy. Okay, so there's an or. Now it could be the case that the woman is in great physical shape and she's less than 45, and we would not give chemotherapy in that case. It's just that both conditions are true. Um, but it could be the case that she's less than 45 but not in great shape, but the clinician still might give the chemotherapy. You see, so or the main thing in the or is that at least one has to be true. Now, there is something called exclusive or, either or, in R, and basically all programming languages. So this is more of how we use um, or in natural language, where we're saying one of them has to be true. Let me see here. So Uh, firstly, note that there is no operator for exclusive OR. It's expressed as a function. That's okay. Here, with the OR and the AND operators, it's just that R expects that the operand 1 will be on the left-hand side and operand 2 will be on the right-hand side. In this case here, it's a function, and so the two parameters, because it's a binary um, operator, are expressed inside of there. So exclusive OR says that exactly one of the two have to be true. Now, in this case here, I'm true and you're false, so it's going to be true. In this case here, I'm true, but and you're true. But what happens there, which is different than or, is that it's false. In this case here, I'm false and you're false, it's going to be false. So that's the same as or. At least somebody has to be true. Otherwise, it's false. But if everybody's true, that's also false. Okay. Otherwise, if one of us, exactly one of us is true, it's okay. So sometimes, what would be a good example of that? Um, well, uh, in natural language, we might say either take Highway 7 to go to Toronto or take Highway 401. So you can't take both at the same time, right? I mean, it's just physically impossible. So we know that one of the two has to exist. So either we're going to the cinema tonight or we're going to the bar, right? We know that we can't do both at the same time. It's just physically impossible. If we go back to our breast cancer data set, it's sort of like saying, um, uh, let's say, if either the patient is male or postmenopausal, then I will use tamoxifen. So here, the patient, if they're not male, they can't both be um, male and postmenopausal, right? So basically here, if they're male, I'll use tamoxifen. If they're women, I only use the drug if they're postmenopausal, okay? So it's a little bit of an abstract example, but you'll see that the either or comes up in lots of different contexts as we move along. Okay, so I want to end today talking a little bit about class of our objects in R. So all objects in R have a class that includes variables and constants and functions and all sorts of things. In fact, I should really write in here, etc., etc. Okay, so I can ask, what is the class of pi? Okay, so when I do that, I get back numeric. So we can think of that as being numeric as being a real number. Okay, the class of 5. Well, we know it's an integer, right? So an integer is numeric, but um, it's also, well, all integers are real numbers, but not all real numbers are integers, right? Integers are just whole numbers, negative or positive. So the point here is that when I pass as a parameter to the class function, R tells me what that that object is, what type of object or what class that object is. That's how it's represented in the computer. And okay, so we don't necessarily in this course care too much about these sorts of formal type, what are called type systems. Um, in and of themselves, except that sometimes as you guys start to write larger programs, you'll need to debug. You'll need to go in and lift the hood on your program and understand why it's not behaving the way that you would hope it would behave, right? So you need to start to look at how that data is being represented in the system. And so I think it's good that you at least are aware that the objects that you have all have a different class. It can be logical, true, false, like these guys here, right? If I run that, um, the class of king is going to be character. And if I have two variables like x5 and y is assigned 7, I can ask what's the class of x equal to y. Now let's evaluate that one, right? That one's interesting. So x is a variable 5 and y is a variable with 7. And then R has to evaluate this expression that says class is equal to y. So is x equal to y? And then give me back the class of that. So how does R evaluate that? Well, it comes in and says, okay, I know what the class function is, but I need to resolve this expression first. I know what x is, so it's 5. I know what this equal is. It's just asking me, are these two objects equal? And y, yeah, I know what y is, and its value is 7. So now R has to evaluate this. It's simplified it a little bit. So is 5 equal to 7? Well, the answer, of course, is false, right? It's illogical. And so then what is the class of false? It's logical, all right? You understand that? So here, this was a Boolean expression, or sorry, a logical expression. Mathematicians would say Boolean. And it evaluates to either true or false. But regardless of whether it evaluates to true or false, the class of this value false is logical. Let's see. And if you don't believe me, then I can come in here and I can see that it says logical. Okay, so we can have more complicated data structures. These are called, let's call them objects for now. Okay, so let's, for example, the tidyverse. We used this last class, and that's the tidyverse has the ggplot nice visualization tools. Here I just loaded the tidyverse package, and then I made a little bit of data available for you. So if you go over here to project and data, you'll see there's this file, a file called genetic-code.rdata. So I can load that into memory. And when I do that, now in my environment, I'll see that I have this genetic code. And it has 64 observations, 3 variables. Okay, so, and I can click on that and I'll see up here a nice view. When I click on in the environment on an object, it basically executes the view function. And see, I can see here that it's amino acid in one column, the codon for that amino acid in the middle, and then basically the counts of different amino acids across 8 different amino acid polypeptides, right? So I observed, for example, I don't know, 93 arginines coded by this particular codon, right? So it's just a small example. Now I'll go back to my code. I can ask what is the class of genetic code, and I'm going to get back something that looks really weird. You'll have to trust me right now that TBL stands for Tibble. And that's the same kind of data structure as we saw for the breast cancer BRCA small BRCA data set. Tibbles are these two-dimensional Excel sheet-like spreadsheet things, right? Um, Now, there's all this other stuff here, and I don't think you should worry about it. This does require a little bit of explanation because I think students find this a bit confusing at first. Data frames have been around since the beginning of R, right? So they were the original data structure that was this Excel-like spreadsheet. Um, but there are some problems with them, some things that weren't very like convenient. And so when Tidyverse came out, this package within R, it created the Tibble, which is like it took all the good things from data frames and got rid of all the bad things. And so you can think of Tibble as being a fancy data frame, but it's still essentially a data frame. So R still sees it. It sees it as a Tibble, but it also sees it as fundamentally a data frame. It's a little bit confusing. And if I use ggplot, I can make really quickly a little plot. Here's a bar chart of all the amino acids along here, and then the number of observations for each of those different amino acids. Note here, well, you saw this last time. Here we're specifying what data to use. This is our aesthetic. Um, and then we have in here some stuff we didn't see last class, stat equal to identity. We'll talk about those later. Width dot equal to dot 5 just means it's a half centimeter, the bars. The color is tomato 3. I labeled my plot. I didn't show labels last class, but here I labeled the title to be ordered bar chart. And one nice thing is that I played around with the labeling on the x-axis so it's a little bit angled, and that's sometimes kind of helpful. And V adjusted just moves the labels to and from the graph, just controls how close the A is to this to the plot. Okay. All right. So I think that will end there. Uh, I hope that that was helpful. Um, I believe it's chapter 4 in the textbook that covers many of these ideas. I would recommend um, working your way through this example and the chapter in the textbook and see if you get stuck. And then, the lectures and the tutorials or the labs are times where we can talk about this. Okay, thank you very much. Today, and you feel a little bit more comfortable with R and R Studio for that matter, I'll leave you with some points of reflection. But in addition to that, I wanted to emphasize that the labs are there to help you learn how to program, and so are the lectures, really, lecture times when we can discuss. Also, there are great resources online for learning R. I've put some links into the reading and the class notes, um, DataCamp, and several others sources, some of them private, most of them not publicly available, I mean, freely available. You should make use of them if you don't feel comfortable. Uh, I'll try to give you lots of little exercises and challenges as we go along. Of course, I do recommend working on the little assignments that they have in the textbook. That's also another good source of practice. Good luck.